Okay, let's move to a more common case in practice, free by free matrix. Find the inverse of matrix B that has the following elements: 2, 5, 7, 6, 3, 4, and 5, -2, -3. Okay, the algorithm is exactly the same as for 2 by 2 case. So we need to use the formula B -1, it's an inverse, is equal 1 over determinant of B and times transpose of complement. Oops. Okay. So, step number 1. Yet again, find the determinant of the matrix. So, 2, 5, 7, 6, 3, 4, 5, -2, -3. So in my previous videos, in the same playlist matrix, you can find the recording how to find determinant in 2 methods. So I'm going to use the method of triangle here, but you can go over the second method and use the second method. It doesn't matter. Or, okay, I'll use the second method here. So we are scratching, let's say we take the first element, right? Scratching, taking 2, and then crossing over that column and row, and we are getting 2 times whatever left, 3, 4, -2, -3. Next. I did wrong thing, I shouldn't clean. 2, 5, 7, okay. Next, we are doing -5. This is this one. This and this scratching, and I will have 6, 4, 5, and -3, right? Left over. So it's gonna be 6, 4, 5, and -3. Plus, I am scratching 7, and I will have left 6, 3, 5, -2. Seven, 6, 3, 5, -2, and as a result, I am getting twice -9 plus 8 minus 5, -18 minus 20. We are just finding determinant for 2 by 2 matrix, which means we multiply by diagonal, first diagonal, and then subtract the second diagonal product, right? Which means in this case 6 times, let me see, 6 times -3, we get -18. And then minus 4 times 5, we get -20. Well, negative because we do minus, we subtract. Okay? Next, plus 7 times -12, -15. And the result is going to be -2 plus 190 and minus 189, and we get -1. Okay? So, determinant B is equal -1, which is not equal 0. which means that everything is fine and the inverse matrix does exist. Okay, second step. Find the matrix of minors. We need to find minor matrix that is going to be 3 by 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. We need to fill out with 9 elements. Okay. So first one, let's take original one, B. What was our B? 2, 5, 7. 6, 3, 4, and 5, negative 2, 5, 5, negative 2, negative 3. Okay, what we are doing, remember, first element, crossing the column and row where element is located. So you can do it in your mind. You don't have to necessarily cross like that, but I'm doing to show. And we are getting, so all right, and this is gives us 3, 4, negative 2, negative 3. 2 by 2 determinant. Okay, next. We are not filling out yet because we are working on operation. So determinant is equal 3 times negative 3 minus negative 2 times 4, and we get negative 9 plus 8 equal negative 1. Now this negative 1 is coming to the first position. 1 star okay. Next, B is equal to 5, 7, 6, 3, 4, 5, negative 2. Okay. Oh, here is negative 1, sorry. Okay, so as you may realize, there are 9 2 by 2 determinants that need to be computed. The process, of course, is time consuming, but the case is not the most difficult. It can get worse if we take much larger matrices. Okay, so well, to consolidate, I'm going to find one more minor in this determinant. The rest you wanna try to calculate yourself. So I'm going to take this position, let's say, position of negative 2, and this, right? So I will have 2, 7, 6, 4, correct? Actually, why I'm cleaning, let it be. Okay, so it's gonna be, we are going to use this one and this one, which is gonna be 2, 7, 6, and 4. So we will have 2 times 4 minus 6 times 7. and it's equal 8 minus 42, and it's equal negative 34. And that number will come where the position of negative 2 is, right? So m is equal negative 1 star star here I place negative 34 in the position where negative 2 is. Yes? Okay. So to calculate the rest of the minors yourself, you should receive the result m is equal negative 1, negative 38, negative 27, negative 1, negative 41, negative 29, then negative 1, negative 34, negative 24. Okay, a matrix of minors of the corresponding elements of matrix B. Okay. The fact that all elements in this matrix of minors turn to be negative, it's purely coincidence. Okay, don't make any conclusion from this. And next we are going to find algebraic complement. How we are going to find algebraic complement? So, step number 3. So, in a case of a 2 by 2 matrix, we know that we are changing the sign for these two, right? But since we have now 3 by 3, let me add so we are going to change sign strictly for the following elements. Oops. It looks like rhombus if you connect them, right? If you imaginary connect, you will see. So, in this case, we are going to have negative 1. Here is going to be positive 38. And then let me use different color. It's not seen well. Okay. And negative 27. And again, we are using here 1. This is 1. And then this is positive 29. And it's here, it's going to be positive 34. Okay, so the rest is going to be the same. Negative 41. Okay, negative 1, negative 24. Okay, this is the matrix of algebraic complement. Okay. Let me rather clean this because this is already B complement, okay, of the corresponding element of matrix B. Number 4, finding transposed matrix of the complement. So B transposed is going to be negative 1, 1, negative 1, 38, negative 41, 34, and negative 27, 29, and negative 24. Okay, transposed matrix of algebraic complement of the corresponding elements of matrix B. And number 5, meaning fifth step number 5. So we are finding the inverse, which is equal 1 over determinant B times transpose of complement. And from here, we are going to get how much is our determinant. It was negative 1, right? Yeah, here it is, negative 1. Okay, so it's going to be negative 1 over 1, right? I'm just writing like that so you can know what I'm talking about. And here we get negative 1, 1, negative 1, 38, negative 41, 34, negative 27, 29, negative 24. Okay, and we are getting, since it's only negative 1, so I can multiply, which means I'm going to flip the sign on every single element. 1, negative 1, positive 1, negative 38, positive 41, negative 34. Let me move a little bit. And getting positive 27, negative 29, and positive 24. Okay, so let's check if we did operations, all operations. This is indeed the correct inverse version of original matrix. So B times inverse. By the way, this is one of the few cases when you can permutably apply B times B inverse or B inverse times B. Okay, and we are getting our original 1, 2, what was that? 5, 7, 6, 3, 4, 5, negative 2, negative 3. Okay, 2, 5, 7, 6, 3, 4, and 5, negative 2, negative 3. And we multiply by inverse, which is going to be 1, negative 1, 1, negative 38, 41, negative 34, 27, negative 29, positive 24. Okay, let's multiply. It's going to be long multiplication, so collect all your patience. So what we are doing, multiplying these 2, multiplying by 1, and then 6 multiplying by no, I'm sorry, not 6, 5. So it's first one we go by row, a second one by column. 5 times negative 38 and 7 times 27. And then the second one, it's going to be 6 times 1, 6 times negative, 3 times negative 38, 4 times 27. Okay, so let's do it. And then the third row, same way. Okay, so we have 2 times 1 plus 5 times negative 38 plus 7 times 27. So second row, it's going to be 6 times 1 plus 3 times negative 38 plus 4 times 27. And the third one also, the third row in the first matrix multiplying, or in original matrix, multiplying by the first column in the inverse matrix, right? So first times 1 minus twice negative 38 minus 3 times 27. Okay. So let's fill out second column. So the same way we are going to take the first row of the original matrix, and this time we multiply by second column, and then second row by second column, and third row by second column. Okay, we are getting 2 times negative 1 plus 5 times 41 plus 7 times negative 29. So actually this negative 141 I can rewrite here. And just here write down just the second row of the original one, 6, 3, 4, and then third row of original one, 5, negative 2, negative 3. Yes? Okay. And the last one, let's do the last one. I'm going to use again the first row, second row, and then third row from the first matrix and multiply by the third column. Okay, so I can do this way. 2 plus 5 plus 7, and then 6. Okay, I need to leave some space here. 6, 3, and 4, and then 5, negative 2, negative 3. Maybe I should move a little bit further. It's not enough. Okay, so all this multiplying by the third column times 1. Since it's negative 34, so I put negative 5 times. See, it doesn't look good. Hold on, let me fix it. Doesn't have enough space. I will shift the third column also. No, not a big deal. So minus 31 times, 34, I'm sorry. And here is plus 7 times 24. So the same numbers I'm applying here. 1 minus 34 plus 4 times 24. 24 negative 34 times negative 2 and times 1. Okay, we got it. So if you do operation, you are going to get 1, 1, 1, 0, 0, 0, 0, 0, 0. So let's check just out of curiosity. So this one should be 0. So negative 2 plus 41 times 5. It's going to be 205 plus 205. And then minus 7 times 29, it's going to be 203. So 205 and negative 2, it's going to be negative 200, positive 203. With negative 203, we get 0. Okay. You can do the math portion and check yourself. And since we are getting identity matrix, which means inverse is correct. Okay. What else can be interesting? That's it. Oh, very important thing, I wanted to mention this in the previous video. Why do we use inverse at all? What for is inverse matrix? Because we don't do division with matrix. Therefore, this is the way indirectly we kind of dividing, meaning multiplying by inverse. Okay? So this inverse matrix method is dealing with matrix method for solving system of linear equation, and we can use Kramer's rule, which already I covered. Okay, finding the inverse matrix for the 4x4 matrix is not considered, since such a task can only be given by instructor who is sadistic. So, but in cases like that, I believe you can find some calculator that will do for you. All right. Sometimes also the inverse of matrix is required to be found by Gauss-Jordan method, but the second method is it's elementary transformation, and that's what we will do next.